would be very interesting. In this example, so we are looking at implicit differentiation. Here's the example. You have a function, looks like this, x to the fourth plus y to the fourth equals 16. What we need to find is a y double prime, not y prime. And as I said, this is a doozy. This is something. Implicit differentiation, take the derivative of everything. Okay. Today, I'll use the prime notation. Yesterday, I used ddx, right, the Leibniz notation. Throughout the course, we kind of use the different notation interchangeably. So, Leibniz notation will be ddx of x to the fourth plus y to the fourth equal ddx of 16, or using prime notation we can say that x to the fourth plus y to the fourth prime equals 16 prime. Of course, the right side is equal 0, the derivative of 16 is 0. Again, the weakness of the prime notation, it doesn't tell me, going back to John's question, with what variable, with respect to what variable we differentiate. Here, it's clear. We differentiate with respect to x, because we have a choice. We can take the derivative with respect to y. So it's important to know that. So by default, we're going to say if we have prime, we differentiate with x. But this is kind of weak notation. Okay, this specify the variable of differentiation. Anyway, look at the left side. The derivative of x to the fourth by the power rule, it's 4x cubed. What about the derivative of y to the fourth? In a second, the derivative of y to the fourth, if we differentiate with respect to y, it will be 4y cubed, right? The dy of y to the fourth. But we need ddx. So we need to also multiply it by the derivative of y, which is y prime. And all of it equals 0. Go ahead, Kathy. No. If you use it correctly, it doesn't matter. But I'm not completely happy with this one. Even though I wrote it myself here, because, as I said, this doesn't tell you, well, I wrote it because before that I said ddx, so I know that I'm differentiating with respect to x. But if I did not have this, the derivative with respect to x, it's kind of with respect to what? But because normally we assume that y is a function of x, but here we cannot assume so. This is an implicit differentiation. This doesn't mean this curve is not necessarily a function. Y is not necessarily a function of x. Indeed, it is not. It won't pass. The graph of this curve will not pass the vertical line test. So we cannot necessarily assume that y is a function of x, but by prime notation we assume that we are seeking dy dx. That's what I wrote here. I want double prime, so I'm looking for the second derivative of y with respect to x. So let's continue to work on this one. We can divide everything by 4, and we can get a y cubed times y prime equals. Actually, I'm gonna keep it. X cubed plus y cubed y prime equals 0. I'm gonna keep it because I'll go back to it, and then finally we'll solve for y prime. So we subtract x cubed, move it to the right side, and we divide by y cubed. And this is the first derivative. However, we need to find the second derivative. Now we have a choice here. I can go ahead and take the derivative of y prime to get y double prime, or I can go back right here to this equation and do implicit differentiation one more time. And I choose to do that one. I'll go ahead and say, now I want to take the derivative of x cubed plus y cubed times y prime equals 0. I'm going to take the derivative of this equation. So this is a second implicit differentiation. And again, the derivative of x cubed with respect to x is 3x squared. Now here I have a product rule. Okay, so let me do it in red here. The product, let's say this is u and this is v. Okay? So what is u prime? U prime will be the derivative of y cubed. Well, the derivative of y cubed will be 3y squared times the derivative of y, which is y prime, right? So this is u prime, and then I need to multiply it by y prime, which is v, and then plus u, which is y cubed, times the derivative of y prime, which is y double prime. And then the derivative of 0 is still 0. So what I did is the product rule right here in red. Does it show red on the screen? Okay. And now let's see what happened. Let's collect 3x squared plus, look what we have. We have 3y squared, and then y prime times y prime. So we have times y prime squared, and then we have y cubed times y double prime, all of it equals 0. What we're going to do next, we want only y double prime. We know that y prime is negative x cubed over y cubed, so I'll take this expression right here and I'll substitute it with negative x cubed over y cubed, like so. Remember, I need to square the damn thing. So, so now we have 3x squared plus 3y squared, and then we squared the negative x cubed over y cubed, and we have x to the 6 over y to the 6 plus y cubed times y double prime, all of it equals 0. And something we learned quite a bit early, when you have a fraction, what you want to do is eliminate the fraction by multiplying by the denominator. After simplification, you see y squared and y to the 6. Well, this will give me y to the 4th right here. And if I multiply everything by y to the 4th, this is what I'll get. I'll get 3x squared y to the 4th plus 3x to the 6, and here I have y to the 4th times y cubed, y to the 7th times y double prime equals 0. Are we doing good so far? Well, if your head is not spinning yet, let's move to the next page and continue. I'll keep the top one just to stay on track here. So now I want to isolate y double prime. So on the left side, I'll keep y to the 7 times y double prime. On the right side, I'll have negative 3x squared times y to the 4th plus minus 3x to the 6. Okay. And then let's factor y double prime. Let's do this. First of all, I have common factors on top. One will be the negative 3, right? And the other, you see, I have x squared, and I have x to the 6. So I can factor the x squared. And on top, I'll have, we factor the negative 3x squared, so we have y to the 4th. And here we have plus, after factoring 3x squared, what's left is x to the 4th. And everything is divided by y to the 7th. And maybe it appeared to you that we are done, right? Are we done? The answer is no. The answer is no, because if you look carefully where we started and where we are now, there is a nice way to simplify the result. Again, look carefully where we started and compare it to where we stand right now. Anybody see that? Okay, give me a hint. Can we do something with the quantity that I point out in the parentheses? Well, it's x to the 4th plus y to the 4th, which is not exactly so. Who said so? Very good, Amanda. We look at where we started. X to the 4th plus y to the 4th equals 16. So y to the 4th plus x to the 4th equals 16. So we can write it's equals to negative, well, 3x squared times 16 over y to the 7th power. And the simplified solution will be negative 48 x squared over y to the 7th. And this is something that you'll see, perhaps even the next lab. But when you do implicit differentiation, in particular, when you take the second derivative, at times you'll find the original equation, the original relation, hidden in the solution, like x to the 4th plus y to the 4th in this case. And this leads you to a significant simplification.